is I want it to be either Wednesday or Friday. I don't want it to be Monday. But if there's any major reason why it shouldn't be either Wednesday or Friday, I'm happy to hear those reasons. You have a reason? Perfect. Wednesday it is, unless anyone's really angry about that. So you can blame the track team. But let me write that down. Test 1. Let's get her done. So I'll make sure that there's a practice test available. I was looking at my old exams, and I have, like this is about the right place. So we're in the right place. So test 1 is just a little later than I'd hoped. So I apologize for that. So test 1 will be next Wednesday. Let's see, 12? 212? Oh, no, yeah, this is the one for before spring. So, yeah, so it's going to be, instead of having 3 exams, we'll do 2, and then we'll have to negotiate over exactly how that gets calculated so that it doesn't harm anyone. But hopefully it's late enough and it'll be fine. Yeah, whenever I change the syllabus, generally I will do like this. There's one fewer test, and so I'll figure out multiple ways to calculate your grade, and I'll give you the higher of the 2 or 3 or whatever it is. Okay, so there's that, number 1. Okay, so today we're going to move into what's called polynomial interpolation. This is kind of a fun little game that we can play. And so before we actually play the game, we'll talk about why. Why is it that we want to do? So we're changing gears. We're no longer going to look at least not for the time being, not going to look at solving equations. We've done that. They'll be on the test. You'll see. I'll give you some practice problems. But why polynomials? Well, calculus is easy with polynomials. You know how it is. Once you throw a sine or a cosine into something, everyone loses their minds. So polynomials make things easy. They can be evaluated easily. They're easy. They're fun. And so, oh, no. So here's the idea. Here's the game that I want to play is if I have, and this is one of these things from analysis. I guess that's this, and that's just, if you, in real analysis, which is like proving everything in calculus. Real analysis, we learn that if you have n plus 1 points, you can uniquely describe a polynomial of degree n. So for example, and here I'll let you play the game as well. If I have 1 point, that point there, which is the point 2, 3, there is a polynomial of degree 0, only one of degree 0 that goes through that point. Do you know what polynomial that is? Can anyone? I mean, once we get the first one, the rest of them are going to be easy. What's that? Almost. That would be a straight line straight up. Y equals 3. Yeah, y equals 3 is the polynomial of degree 0, and that's the only polynomial of degree 0 that goes through that point. So this is y equals, or better yet, let's call this f of x equals 3. Now, in a similar way, if I put a second point up here, 2 points uniquely describe a linear of degree 1 polynomial. So let me just put up another one, and then, here, let's see, I'll do this. Yeah, I'll make it easy on you. So we'll do this point. This is the point 0, 2. So I want to know, what is the equation of this polynomial? Degree 1 polynomial, which means that it has an x to the first. So degree 0, there's no x. It's just a straight line, horizontal. What about this one? Anyone know what that is? There's only one line that goes through those 2 points. Ooh, very nice. Almost. Wait, y equals, just a minute. Y equals x plus 2, is that what you said? Okay, there's a coefficient that's missing. You want to see what it is? You got it? 1/2 x, yeah. It's because of the way I drew it, it's hard to see, but yeah, that's actually, the slope is 1/2, very nice. So slope is 1/2 x plus 2. Okay, well, if this is true, and that's all this slide says, it's just a gobbledygook about the fact that if you have n plus 1 points, you uniquely define an nth degree polynomial. So given that, we could do polynomial interpolation the hard way. So for example, I could take those 5 points and figure out a polynomial. But how am I supposed to do that? That seems really hard. And so one way I could do it is I could do something like this. I could say, here's a 4th degree polynomial. And then, wait, that's, why is there a j at the end? I don't know what the j is doing there. Yeah, ignore the j. Yeah, so ignore the j. Anyway, I could have this polynomial and I could say, okay, what is p of 1? Because p of 1 should equal 1. In other words, 1 should equal, oh wait, I don't like this color. 1 should equal a4 plus a3 plus a2 plus a1 plus a0. And then 3 should equal 16a4. I'm just taking that point and plugging 2 in for x, and the result should be 3, shouldn't it? Plus, let's see, a3, sorry, 8, a3, 4a2 plus 2a1 plus a0. Ignore the j. Well, you kind of see that this is going to be somewhat tedious. When I plug 4 into this, I should get 2. When I plug 5 into this, I should get 1. And when I plug 9 into this, I should get 6. I will have 5 equations, 5 unknowns. I don't even think Dr. Brad would be happy with this linear algebra. I'm sure you could do a 5 by 5. Does he make you solve 5 by 5 equations? Never? Well, your calculator could handle it, couldn't it? I'm sure it could. But that's so, I don't want to do it. So let me show you the trick. First of all, I'll do the trick over here like magic, and then we'll do the trick together. So let me show you the trick using 3 points. And just to show you that it's completely, it doesn't matter what points you pick, I'll just pick 3 people to tell me your points. And I just need 3 points, whoops. So Alyssa, Breyer, and Matthew. I just need points, a point. So Alyssa, pick a point, any point. I'm sorry, 2, 7? Yeah, very good. So 2, 7 works. So 2, 7 is Alyssa's point. Now, the only restrictions now that Matthew and Breyer have is because this is going to be a function, I can't have 2 as your x value. So, but Breyer, do you have another point you want me to use? 1, 1? Okay, thank you for a nice easy point. Matthew, you can't use 1 or 2 as your first number, but anything goes. 3, 4 looks good. Yes, so 3, 4. So here's the deal. 3 points. I should be able to come up with a parabola, a degree 2 polynomial. And so let me just graph these. Ugh, that's not terrible. Here is my graph. We have 1, 1, 2, 7, over 2 and up 7. I'm just going to eyeball this. And then over 3 and up 4. There they are. So there's my 3 points. And supposedly, these uniquely define degree 2 polynomial. It's probably going to look something like that, probably better than what I just drew. So here's the trick, is that I can sort of force this to work by doing this. I know that I want, when I plug 2 into this, I want to get 7 out of it. So here's what I'm going to do, is I'm just going to do this. I'm going to call f of x, or maybe call it p, because it is a polynomial. And I've got this in the PowerPoint here, but it's just so amazing that it's so easy to do this that I got to show you with just some points that you picked. So p of x, I want this to equal 7 whenever you plug 2 into it. And so what I'll do is I'll put a 7 there, and then we're going to doctor that up in just a minute. I want it to equal 1 when you plug 1 into it. So that's this point. And I want this to equal 4 when you plug 3 into this. Now the trick is that I only want this to equal 7 when you plug 2 into this function. And so what I could do is I could multiply this 7 times x minus 1 times x minus 3. Now let's just see what this does for a minute, is that if you plug 1 into this function, at least the way that it is so far, when you plug 1 into this function, this will be 0, and so this gets ignored in the polynomial. When you plug 3 into this function, this will get ignored. However, we have a slight problem, and that is that when I plug 2, ignore the rest of this for just a sec. When I plug 2 into this, I get 1 times negative 1, which is -7. And so to correct for things, I'm going to divide this whole thing by 2 minus 1 times 2 minus 3, so that when I plug 2 into the top, I end up with just 1 times 7. Now, let me just show you this trick again. So if I plugged 1 into this particular function, I want the output to be this one right here, but I want this 1 to be ignored when I plug 2 or 3 into this function. So I'll just do that. 1 times x minus 2 times x minus 3, so that if you plug 2 into this, you get 0 here. If I plug 3 into this, I'll get 0 here and there, by the way. And then let's just divide, same deal, so that I can correct for any errors, or not errors, just scaling that has occurred. I'll just divide by 1 minus 2 and 1 minus 3. We're going to do the same thing with the first one. We'll formalize this in just a minute, but this is going to be x minus 2 times x minus 1 all over 3 minus 2 and 3 minus 1. Now, fortunately, you guys were kind to me and picked relatively easy numbers to work with, so that my polynomial is something that I can pretty quickly simplify here if you just bear with me. 4x plus 3 plus x squared minus 5x plus 6. Almost done. Hold on, I need to move this over. Plus 4 halves times x squared minus 3x plus 2. There it is. Well, I'm not going to keep simplifying, but you can see that you could collect like terms. For example, there it looks like there is, it's negative 4x squared. I don't know what the rest is going to be, but you could collect all the like terms, and you'll have a degree 2 polynomial. And when you graph that degree 2 polynomial, you're guaranteed that it will go through these 3 points, the 3 points that you picked. That's all we're doing, is we're trying to, this unit is how do we figure out, find a polynomial that will interpolate. Now, there's uses for this, so not to worry. We're sort of straying from calculus just a bit, but we'll talk about the uses after this first test. Let me go back to PowerPoint land, and then we'll see how this, if you plug and chug, yeah. Okay, so what we just did, this is the easy way. Those are called Lagrange polynomials. Lagrange polynomials are just these polynomials that are constructed in such a way so that they are 0 at every point of data that you have, except for your special point, whichever point. You probably could see what I did to make those, but here is, that's another method that we're going to go over later. Okay, so here are the Lagrange polynomials. So these are the building blocks. I'll explain exactly how to construct these, but you can kind of see where they came from. Those correspond, by the way, they correspond with these data points back here. Let me get rid of all my stupid pen there. So these data points, you have x equals 1, x equals 2, x equals 4, x equals 5, and x equals 9. I want to have these building blocks, these Legos that I can piece together based on those. So you see, you have 1, 2, 4, 5, 9 here. So you get rid of the 1, and you make these sort of factors, multiply them together, and we'll talk about that fraction out front, but you kind of saw where it came from. Anyway, you're going to piece these together in a very special way. Let me show you the graphs of these. Here's what's special about them. This is a polynomial. This is the first one. We'll go back here. So that first one, the one I'm naming L sub 0, that's this one here. What's special about it is that at 1, the function value is 1, and it's 0 at all of the other points. This is an actual graph of that polynomial. I can show you the other polynomials. They aren't going to be that exciting, but just to show you, this one's the second one. This one is 0, or 1 here and 0 everywhere else. So these are all 4th degree polynomials, and they have these special properties. And then you have the next one, and the next one, and the next one. Yeah, the last one, I guess, is kind of interesting because it's 0 here, 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 and then it's up to 1. So you have these degree 4 polynomials that fit the bill. Once you have them, you can just put them together however you want. And in this case, we want to put them together this way. So let's actually see how this works in real life with a real example. So let's see. No. Okay. I guess I'll go back here. I don't have a good example. We need another. Let's go with 4 points, and I'll walk you through this very slowly. It's not that hard. So we'll get 4 points. So let's see. What can I do here? No, I'll just make up. I hate to say that I'm making up random points because they're not really random. Okay, so 1, 5. Oh, we could take the date. What is it? It's 2. What is today? The 4th or the 5th? The 5th. Okay, so 2, 5, and then we can take. Let's see. Let's go with 4, 4, and one more point, maybe 5 and 10, just to make it different. How's that? So we've got these 4 points. I want to find a cubic, a 3rd degree polynomial cubic that goes through these 4 points. So here's the Lagrange polynomial formula. Lagrange polynomial is equal to, I'll write it down and then we'll actually do it. So it's x minus x sub I. We'll do this L sub I. I'm sorry. That's not right. X minus x0, x minus x1, dot, 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 x minus xi minus 1, x minus xi plus 1, dot, 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 x minus x in. I know that's really kind of ugly to look at, but when we do it, it'll become more obvious as to what this means. And then we're going to make this into a fraction and basically divide by x sub I minus all of these factors. So you just got a bunch of factors. And so this particular polynomial, you can see that it will be 0 at x0. It'll be 0 at x1. It'll be 0 at every x except for x sub I. It'll be 0 at x sub n. So let's actually do this. So this Lagrange polynomial will do L sub 0 is going to be x minus 2 times x minus 4 times x minus 5 all over 1 minus 2, 1 minus 4, 1 minus 5. I'm just going to simplify this a little bit, make it a little bit easier to understand. Wow, someone's angry. Okay, so let's see. 1 minus 2 is negative 1. 1 minus 4 is negative 3, negative 4. So negative 3, negative 4 is 12, negative 12. There it is. Okay, see if you can come up with L sub 1. So the way we're numbering these is this is x0, this is x1, here's x2, and here's x3. So take a minute, see if you can do L1, just to make sure that it makes sense to you. Then we'll work it out. I suppose I could just use my computer to expand this. Let's see. Yeah. Okay. Well, I'll just keep track on the computer. Bless you. All right, let's see how we are doing. Let me just change this one thing here. There we go. Okay. All right. Curious to see how we did. Oh, I'll pick a rando. The next random person, Cooper. Cooper, what do you think L1 is going to look like? Is it going to look like L0? Probably. I mean, you see the pattern with L0? Yeah, let's walk through it. So we're going to have factors, and with L1, we want to protect this. This is kind of the one that we don't want to include in the factors. So you want to have a factor. So just to compare this with L0, notice that with L0, we protected this. And so you have the 2, the 4, and the 5. So go ahead. You want to tell me what factors you have for L1? Very nice. Very good. Okay, so that's the top of that one. And now let's see if we can get the bottom. Briar, do you know what goes below all that? Yeah, and that's because if we plug 2 into this, so we know that we'll get 0 if we plug 1 or 4 or 5 into this, but when we plug 2 into this little building block, we want the answer to be 1. And to get that, you're going to have to divide by all of this so that when you plug 2 into it, you do get 1. Very nice. And so I'm just going to type this into my computer so that I keep track. Okay, so this is going to be divided by 1 times 2 times 3. Is that right? So 6. Okay. All right, we're halfway there. So next one is very nice. Okay, yeah, they get kind of ugly looking. I'll show you once we get done. So let's see, L2. Let's see, where's my randomizer? Next volunteer. Oh, I know you could do it, but you're not here. Grayson can do it, though. What do you think L2 is? All right, that's beautiful. 4 minus 2, 4 minus 5. Okay, so then that's going to be that stuff. And on the bottom, it's 3 times 2 times -1. So -6 on the bottom. Let me just fix this so that I have it. And then I've got this here. And this is L2. Like I said, I'll show you what I'm typing. And I'm cheating. I'm not using Python because I didn't have it all ready. And then one more is L3. One more here. We'll put it all together. Final volunteer. Oh, you're not here either. Eli's here, though. Eli, what do you think of L3? Very nice. Okay, so let's see. This is going to be 4 times 3 times 1 on the bottom. So that's 12. Okay, very nice. So let's see. This thing is, we just fix this and get rid of this. Okay, yeah. Okay, so I've got them all. They're really ugly, though. Here they are. So there's all of the, I know it's kind of small, but here, I'll make it bigger. Doesn't get any better when it's bigger. But what we can do is we can see what these things look like. X equals, let's see, 4, just to see how this works. So if we plug x equals 4 into L3, let's see what happens. You get 0. And if you substitute x equals 5, then you get 1. That's what we want. That's what we want with this. Okay, we're almost there. Now we take these, those are the building blocks, and then the key is that once you have those defined, and of course we're doing this on a computer, which we'll do in Python next week maybe, but maybe after the test. We'll save it for after the test. What we're going to do is we'll have the computer keep track of all the ugly stuff, and then you'll just be able to tell the computer you want to take L sub 0 times f of x0 plus L sub 1 times f of x1, and so on down the line. And the reason that this is going to work for us is that we're going to have a polynomial. The function value, when you plug the first x0 into it, you're going to have, here's what this will look like. When you plug x0 into this polynomial, this thing will be 1, and everything else will be 0. And so the rest of it doesn't really matter. Let's see, L2, L3 times f of x3, and so on. Yeah, this will be 0 as well. And then, of course, which one gets turned on or off differs depending on where it is, what you're plugging in. Let's see what this looks like for this particular problem. So I know this is really kind of big, but I'll do this on the computer momentarily. So it says it's 5, 5, 4, and 10. So I want to do 5L0, 5L1s, 4L2s, and 10L3s. So that is my polynomial. It's a third degree polynomial. And it will interpolate. It'll go through. Interpolate just means that it goes through all of those points. And so here, I'll type that in just a minute. So here's P3 is going to equal, 5 L0, 5 L1, 4 times L2, and 10 times L3. Wow, that's interesting. It got the constant went away. So it must go through the origin. Huh. So there it is. So we can plot this. So plot this P3 between x equals, we might as well go from 0 to 6 just to see what it looks like. And there it is. So let's see. So when x equals, what were our numbers again? We had 1, 2, 4, and 5. So at 1, this polynomial goes through 5. 2, 5. 4, 4. So that's 4, 4. And then 5, 10. Wherever it is. I think I was off. Amazing. I find this to be incredible that you could do this. So, and this is the sort of thing that you really can't teach an algebra student because of, not because it's difficult, but because of the bookkeeping. That's why this is a numerical methods thing, is because we want to do the bookkeeping. Okay, let's see. Where's my next thing? Give me a sec. All right, now there is a cost, or there's something that we need to worry about. And so we need to worry about the errors. Wait, I just want to see, what is this? Oh, that's this problem. They're so supposedly simplified. But so the thing that we need to worry about is the error. How far off are we? How much of an error are we making? And what I mean by error is, if we go back to this picture of this polynomial, this is an approximation of a function that happens to go through these 4 points. And sure enough, it goes through those 4 points, but there's no reason to think that this is exactly what this polynomial looks like. Let me just show you what I mean. Whoops, go back. Here's those 4 points again. You have 1, 5, 2, 5, 4, 4, and 5, 10. Okay, good enough. That's whatever. This is all guesswork anyway at this point. So you saw what that polynomial looked like, but how do we know that's what the actual function looked like? It could look like this. That hits all the points, doesn't it? So here's the polynomial down there, and here's what it might look like. Now, that may be the case that we're off, but here's something that I want to point out, is that how far off we are is much less, so here, much less when you're within your data than when you're outside your data. Like over here, if this is really what the function looks like, over here you're way off. And over here you're also way off. But when you're within the scope of your data, you're closer to the truth. So how far off? That's the question when we say errors. And so interpolation errors, you might guess that we're going to be doing something very similar to what you did when you did, what are they called? The Taylor polynomials. And in fact, it's going to feel very similar. Taylor polynomials, because those are sort of like approximating polynomials, you do this, they are not sort of, they actually are. It's the same idea. So here's the nuts and bolts of how this works. Wait, is this the proof? Yeah, this is the proof. Well, it's okay. So I'll tell you when we get to the end of the proof, all right? So here's the idea here, is suppose you want to use P of A, that's a polynomial, to estimate F of A, that's a function. Then what we could do is we could set up these, this polynomial here, and this polynomial is actually 0 at all of the data points. So that's all that is. And using that, we can compute this expression. Now that expression is just how far away from the truth you are in relation to how far your point is from all the other points. So this kind of gets at the fact that the closer you are to a data point, like if I want to approximate like this point, that's pretty close to another data point. You're probably going to be pretty close to the truth. Whereas if I'm over here in between two data points, far from either of them, you're not going to be as close to the truth. And certainly if you're way over here, you're going to be far away from all the data points. So that's what this does, is it just says how close are you to the truth relative to how far you are away from all the data points. That's what this measures. Anyway, we can take that and we can define yet another function that says that what we're doing is we're going to do the actual function minus the actual polynomial minus this expression times that polynomial. Now, the cool thing about this is that this thing has at least n plus 2 roots. The reason why we know that is because every one of these points, it has a root, because the polynomial and the function match exactly at every one of those data points. And this function is 0 at every one of the data points. In addition to that, where's the extra root? Yeah, I'm not, I think because, it's because of this. If you have A, plug A into this, you get F of A minus P of A minus the quantity of F of A minus P of A, because you're basically canceling out the W. So you have all of the data points are roots, plus A has a root. Anyway, so that has at least n plus 2 roots. The derivative has at least n plus 1 roots. Where is this? And the n plus first derivative has at least 1 root. And we're going to say that this xi, that's what that Greek letter is going to be a root of this polynomial. We're still in proof land here, so we're almost to the actual, almost to where you're going to say, okay, here's what we're actually going to be doing with this. So this we know is true. There is some point, we're going to call it x equals xi, that's that Greek letter. That's where you have a root of the n plus first derivative. And so that's what this means, that this function is just f minus p minus c times w. So we can do that derivative. But this particular function is a polynomial of degree n, so the n plus 1 derivative is 0. And so that kind of goes away. And then also, this thing has a very predictable form for its derivative, and that's going to be just n plus 1 factorial. And the reason for that is because that is a degree n plus 1. Where is it? Go back. There it is. Degree n plus 1 polynomial. This is like x to the n plus 1 plus a bunch of other stuff. So the n plus first derivative, you've basically just taken the n plus first derivative of this, because all the other stuff will have 0 as its n plus first derivative. So that's where that came from. And then just a little bit of algebraic manipulation. C, we know what that is this expression. And so what this tells us is, after solving for f of x minus p of x, we know that the error is going to be equal to this. So this is an expression for the error. I know it looks kind of, well, also it's pixelated. I don't know why. But what this does for us is it allows us to get a bound for the error. We don't know what value c, what value this is, but we know there is a value which will give us the difference, the error. And so we can get a bound on the error. So let's take a look at this in real life. Okay, here we go. There, we can do this. So we'll do this one. what I want to do is I want to focus on the error, the approximate error. So this is mainly useful when you actually know the function. When we don't know the function, like with those data points back here, I didn't know the function, so I can't really approximate the error. But here, when you have a function, you can approximate the error. So we want to approximate this. To do that, we'll do our Lagrange polynomials and everything. So I'm not going to, well, I don't know. This isn't too bad, is it? There's only 3 data points. Yeah, let me switch over to Notability. We can do this completely. This is kind of like what your homework will be like. So I might as well do this one in full. Okay, so let's suffer through this one together. Paste it in there. Okay. So we need our 3. There's only 3, so maybe we can just work these out. L0, L1, and L2. So we need these 3 polynomials. And then we'll get the P of X over here. So let's do L0, L1, and L2 first of all. So L0, let me get it started, is going to be x minus 1.25 times x minus 1.6 all over 1 minus 1.25 times 1 minus 1.6. I know, it's not very pretty, but we can work through. Maybe I can use the computer to keep track. Yeah, it'll be much nicer on the computer. Okay, so this one is going to be x minus 1, x minus 1.6 on the bottom, 1.25 minus 1, and 1.25 minus 1.6. And then L2, hopefully this is, you're just like, yeah, it's just tedious, which it is. The tedium is why it's so good to use a computer for this. Sorry, 1.25. Okay, so this will be 1.6 minus 1 and 1.6 minus 1.25. Let me just see what these numbers look like. Why did I pick numbers like that for my PowerPoint? I have the, just a minute. I want to just see, do I have the answers? No, I don't. That's okay. It's okay. We'll do it. Okay, so I'll just have to pound through. Let me move this over so we don't have to look at it while I'm typing. Right there, so I can see it. Okay, give me a sec. I do have somewhere, I have some Python code that'll do this, but yeah. X minus 1.25, x minus 1.6. Okay, the first one will be the long, oh. Okay, I had an extra parenthesis. Okay, so here's what I'm getting. 6.667 x minus 1.25 x minus 1.6. Move this over. Oh, come on. I'll just erase that. Okay, next one will be quicker since I went to the trouble of typing. So bear with me. Copy, paste. Okay, so the next one is x minus 1, x minus 1.6 over, let's see, 1.25 minus 1. There you go. I think I got this. Okay. Oh, darn, I didn't rename it. Just a sec. There's L1, here's L0, L1, and then L2 is going to be x minus 1.25, x minus 1, 1 minus 1.6. Okay, hopefully this is right. All right, I think I got them all. I don't know if it's important to write these down. I guess I'm just doing it because I want to compare. I want to see what the error. The thing that I want to do though is to approximate the error to show you how you do that. So once I've got these three, I'll do this. The polynomial will be the function value for the thing that I'm approximating, evaluated at 1. So that'll be e to the negative 2 times L0, and then plus e to the, now plug in 1.25. What's that? 2.5 minus 4, so 1.5 times L1. And then the final piece is e to the 2 times 1.6 is 3.2, so negative 0.8 L2. There it is. And then, of course, we could compute. I will do this in just a minute. I'll compute P of 1.4. I guess I could do it right now. So P is e to the negative 2 times L0 plus e to the negative 1.5, as long as I've computed those correctly. L1. Let's see, L2. Okay. Okay, so expand this. Okay, whatever. Yeah, here's the polynomial there. You can kind of see it. Lovely, isn't it? Okay, so I could actually, yeah, I could substitute x equals 1.4 into this polynomial, into the p. I guess evaluate that. And then we could compare this with e to the, what is it, 2x minus 4 up there, 2 times 1.4 minus 4. And you can see that they're pretty close to one another, but I want to know how close can I expect it to be? And so we want to come up with an error bound. So it's the approximate error that we want to work on. And so let's just go back to this slide, get that formula, and we'll see how the formula works. So there's the formula down at the bottom. Let me grab this so that we can copy it and see how it works in terms of this exact problem. Copy and delete. There we go. Okay, so there's the formula there. So think of this as the error. This is how far off we're going to be. So let's go ahead and see if we can do this. It looks like the main issue that I'm going to need to deal with is this right here, the n plus first derivative. Since we're doing a second degree polynomial, I need the third derivative of this thing. So here's f of x is e to the 2x minus 4. I need the third derivative. So that means we're going to go walk our way through these derivatives, first, second, and third. Let's see if you remember your derivatives. I'm pretty sure you do. Let's see, here's my volunteer list. Let me pick another volunteer. All right, Roston, do you know the first derivative? Oh yeah, isn't it nice, e to the x? Zane, what about the second derivative? That's right, yep, 4e to the 2x minus 4. It's like the same thing over and again. Matthew, do you know the third derivative? That's right, yeah, you're just going to keep going, aren't you? Because e to the x is a nice function, so there's not a lot to do. So you've got your third derivative. And so what this says is that there is some point, and that point is going to be somewhere between 1 and 1.6. So here, this c is somewhere between 1 and 1.6. But we don't know exactly what it is. But what we could do is we could think in terms of the worst case scenario. Like, what's the worst that it could be? What's the biggest? What's the largest that f to the n plus 1 could be? So taking that function, hopefully you're familiar with that function. That's a, I mean, maybe not with that exact function, but it's an exponential function. You know what it looks like, you know, it's increasing. So where is the maximum going to be on that interval? Does anyone know offhand? Do we have to do some calculus, or can we just figure it out? So that function goes up. You're all like asleep. Yeah, the biggest is going to be on the right. It's the 1.6. So yeah, because this function looks something like this. I mean, I don't know exactly what it looks like, but here's 1, here's 1.6. There, that's the biggest. So we might as well just plug it in. So that's how we're going to get that. We're going to approximate this. So maybe down here I could just say that the error is going to be less than or equal to what we get when we plug 1.6 into this. So let's do that. F triple prime at 1.6 is sort of the biggest, the worst case scenario, divided by, notice on the bottom up there, you have n plus 1 factorial. So let's do that, 3 factorial. And then times I have to compute all this mess. So how close are we to the point? 1.4 minus 1, 1.4 minus 1.25, and 1.4 minus 1.6. So essentially you're just saying, okay, we're going to deal with this. So one way to think of this is that this stuff looks suspiciously like the error formula for the, the polynomial, Taylor polynomials. You know, you always do the next derivative divided by a factorial. And then all of this stuff is kind of like how close we are to the actual data points. So that's what those are. So let's actually compute this. I'm going to need to use my computer because I can't do, well, I guess I need a calculator. I need something. Let me pull this out of the way. There we go. Okay, so we have the e to the 2 times 1.6 minus 4. So that's f, sorry, I forgot to times 8. 8 times this divided by 3 factorial, that's 6. And then multiply by these 3 factors. So my point that I'm using is 0.4 away from the first data point, and then 0.15 away from the second data point, and then 0.2 away from the third data point. And I don't know, it doesn't have an absolute value symbol, but it should, just so you know. We don't care about negative or positive. We just want to know how close. And so I'm not going to bother with the negative. Whoops. And I got 0.0071. Here I can show you, but here I'll just do this. This is the error is less than or equal to 0.007189. Here, I'll show you this on the computer. Yeah, I need to use Python, but here, this was just quick and easy. Okay, so this is my error estimate. It's that the derivative, the third derivative, divided by 3 factorial times how far we are away. So we can expect that the polynomial is within this of the truth. Here is the polynomial. Here is the truth. And notice that we are within that. Look at this. This is 0.305, 0.301. These are about 4 1,000ths apart. And this says that it will be less than 7 1,000ths. So it was correct. It was the prediction. Now, the reason why this is important is because there are certain functions that perform extremely poorly when you put them into a polynomial interpolation situation. Let me just show you an example. If I were to try to interpolate 1 over 1 plus x squared, and you might be saying, wait a minute, that's your favorite function. Well, not exactly. That's the derivative of my favorite function. So that function, let's say that that is the function that I want to interpolate. Well, let's think through what the derivatives of this would be. Actually, we don't have to think through it. I can just have this do it. I should, so down here at the bottom, we'll do this. We'll do the derivative of this function, 1 over 1 plus x squared there with respect to x. Just do one derivative. Okay, that's nice. Let's do the second derivative. Give me a sec here. There's the second derivative. Okay, very nice. Let me do the 10th derivative, and then I'll explain why this function is so bad when it comes to interpolation. The reason why this is so bad when it comes to interpolation is when you do something like the 10th derivative. So if I had 9 data points, the weird thing about this function is the more data points you have, the worse the interpolation is, because look at what happens to the derivative. The derivative gets bigger and bigger very, very quickly. I think it's like a more than exponential. It's kind of hard to tell from this, but if I plugged a number into this, I don't know what number I'd want to put in, but these get really big really quickly and overwhelm the factorial that would be on the bottom of this particular expression. So I'll actually show you some polynomial interpolations with that, but when we do our Python, that'll be fun to do. Okay, let me just see what else we need before we have to finish. Okay, so using the error estimate, we talked about this. So, and this is, yeah, there's that function there. So let's do the sine of x just to see. Compute the error. That one's a nice, easy one. So the sine. If we have nodes 1, 2, and 4, and we're interpolating the sine, so here's what the sine looks like. Here we go. And when I say nodes, I mean those are the points that we're using for our data. So here's the first one. Whatever 1 is, 1 radian, the sine of 1 is 0.6 or so. 2 is going to be up here somewhere, and then 4 is going to be down here somewhere. So if I take those 3 and I connect the dots with a nice smooth parabola, okay, whatever, then it's not going to be perfect, but it's going to be pretty close in certain areas. So let's see how bad will the error be if we do this. And so the way that we're going to figure this out is we're going to come up with the third, since there's 3 nodes here, and this is a second degree polynomial, I want the third derivative, just like with the last problem. So that's your job. You come up with the third derivative of the sine function. Once we have that third derivative, I will plug that in to this expression. So you get your third derivative. I guess I can pick a volunteer for the third derivative. I think we've been around the entire room, so let's go back. Just pick one. Cooper, do you know what the third derivative of the sine is? Very good. Negative cosine. Okay. Okay, next. I want to know how far off, like here's this little gap here. Can I predict how bad things are? Well, if this is the third derivative, and I'm interested in the third derivative along this range of values here. Sorry, all the way there. There we go. How big or small could the cosine be? What's the maximum and the minimum of the cosine? You know what it is, right? Yeah, it's 1, 1, and -1. Yeah. So when you're dealing with things like cosine, just use the most obvious thing. Don't think, oh, it could be a little bit bigger, a little smaller rather in this range. No. 1 and -1 is worst case scenario. So that's the easiest thing for a bound. And so that's what I'll do is I'll just say, okay, so this thing is going to be less than or equal to 1/6 times this product of distances, x minus 2 and x minus 4. So if, for example, I want to know how far it is off when x equals 3, then I'll just plug 3 into this, and I get 1/6 times, what is this going to be, 2 times 1 times -1, or about 1/3. I know, it's an absolute value. So 1/3. 1/3. So worst case scenario at x equals 3 is that you're off by just 1/3, which is actually pretty big. But that's basically it for computing errors with interpolating polynomials. This last one, we kind of talked about this, so we'll skip the top one. We'll do that one on Python because that one's kind of cool. This last one, compute the error in interpolating a monic polynomial of degree n+1 with n+1 successive integer nodes. All that's going to do for you, here I'll just show you what that means. Monic polynomial is this. Let's see, you have some number times x to the n+1. So that's what we're doing. And then I want to know the error if we use n+1 successive integers as nodes. So in other words, maybe we're going to use 1, 2, 3, 4, ... up to n+1. So those are going to be the points, the data points. Okay, so doing this, you're going to get an nth degree polynomial because n+1 numbers give you nth degree, like 3 gives you a second degree polynomial. So n+1 points gives you an nth degree polynomial. So if we do this, then I need the n plus first derivative, whatever, of this function. So that's what this is getting at, is that it's not going to be perfect, but it's pretty easy to compute. But can anyone see what the n plus first derivative of this will be? Like, all you have to do is think of what's the first derivative and the second derivative, and then hopefully you can think through, oh, it's just going to keep going, right? No one wants to say it? How about first derivative? Like, what's going to happen with that first derivative? A times n+1, right? Times x to the n. And then the second derivative, a times n+1 times n times x to the n-1. Third derivative, yeah, so it's going to be n+1 factorial times a. So the n plus first derivative, n+1, is going to be a times n+1 factorial. And so that's constant. So there's no estimating. This thing really doesn't matter, you know. So you end up with a times n+1 factorial over n+1 factorial. Those cancel, times all of this. So we'd still have to multiply through by all the factors. It'll be x minus 1, x minus 2, x minus 3, x, and so on. So that's actually kind of a lot of error, to be honest. I'm multiplying all those together. All right, let me just make sure there's nothing else recursively defining. Okay, yeah, next time. So there is an even easier way than this. So the Lagrange polynomials, they're easy, but they're not the easiest way to do this. So we'll learn about the easier way on Friday. So this is a good start, though. I need to update the homework just to warn you. If you look at it right now, there's not going to be anything there. So my apologies for that, but I'll get it updated right after my next class. I don't want